Two particles are torn apart and sent to opposite ends of a lab. Measure one, and the other answers instantly. Einstein was certain a hidden code explained it. One experiment has been hunting that code for 60 years, and tonight we follow it everywhere it leads. Starlight that picks the settings, quasar light older than Earth, two labs that end up disagreeing about what happened. If questions like this pull you in, a quick like or subscribe really helps this channel grow. Prepare yourself. We begin. Princeton. In the spring of 1935, Albert Einstein sat down with two younger physicists and wrote 4 pages that would haunt science for the next 90 years. His complaint was simple to say and impossible to swallow. Quantum mechanics worked. It predicted the colours of atoms, the behaviour of metals, the light pouring off distant stars. Every experiment agreed with it, and Einstein, one of the men who helped build it, thought the theory was describing a machine through fog. Here is what bothered him. Quantum mechanics says a particle carries no definite answer until you measure it. Ask an electron which way it spins, and before the question, the answer does not exist inside it. The answer appears at the moment of asking. Reality, according to the theory, waits for you. Einstein found that ridiculous. He believed the answer was already there, written down somewhere the theory could not reach. So he built a trap. Take two particles, let them touch, then fire them in opposite directions. Quantum mechanics says these two can be linked in a way nothing in daily life prepares you for. Measure the spin of the first, and instantly you know the spin of the second. Instantly, even if the second one now sits on the far side of a continent. Einstein saw 2 escape routes, and he despised one of them. Maybe the measurement in one lab reaches across the emptiness and shapes the other particle. That demands an influence outrunning light, which his own relativity forbids. He called it spooky action at a distance, and he said it like an insult. Or maybe both particles left home carrying their answers already. Picture 2 sealed envelopes packed at the same desk. One holds a red card, one holds a black card. Mail them to opposite ends of the Earth. Open yours in Tokyo, see red, and you know at once that the envelope in Chile holds black. Nothing raced across the ocean, nothing spooky happened. The correlation was loaded in at the start and the mail carriers just delivered it. Einstein bet everything on the envelopes. That hidden content is what physicists would later call a hidden variable. A set of instructions riding inside every particle. A code beneath the code that quantum mechanics can only see the shadow of. Look closely at what he was really claiming. He said quantum mechanics is incomplete, correct as far as it goes, and blind past a certain depth. The theory hands you probabilities because it is ignorant, the way a stranger walking into a card game deals in odds while the deck itself is already stacked in a fixed order. For Einstein, the universe kept its books. Every particle, every outcome, every flash on a screen followed from something real and definite that existed whether anyone looked or not. Niels Bohr fired back within months. His reply ran long and dense and famously hard to follow. Even physicists who agreed with him admitted they could not quite pin down the argument. Bohr's position came down to this. Asking what a particle is doing between measurements is a question with no meaning at all. And so, the 2 greatest minds in physics dug into opposite trenches and stayed there. Now here is the part that makes the next 90 years so strange. Both camps used the same equations. Both predicted the same numbers. Every experiment anyone could imagine gave identical results either way. The disagreement was total, and it looked permanently beyond the reach of any laboratory on Earth. For 3 decades that verdict held. Then a machinist's son from Belfast found the crack nobody else had seen. Before you can hunt a hidden code, you have to know exactly what you are hunting. Einstein's envelopes sound clean. Red card, black card, sealed at the factory. But real particles are far more demanding than that, and the moment you look at what a detector can actually do, the envelope starts to strain. Here is the problem. A card holds one answer. A detector can ask many questions. Take an electron heading toward a magnet. You can stand that magnet upright and ask, are you spinning up or down along the vertical? You get an answer. Now turn the magnet on its side and ask about the horizontal. You get an answer to that too. Turn it 30 degrees, 60 degrees, any angle you like. Every angle is a legitimate question, and every question gets a crisp answer. Up or down? Always one or the other, never anything in between. So if the answers were packed in advance, the envelope cannot hold a single card. It has to hold a full instruction sheet. a line for every possible angle you might choose, filled in before the particle ever left. That sheet is the hidden variable. That is the code. And this is a real proposal, taken seriously by serious people. It says the electron is a tiny courier carrying a sealed manifest. Ask it about the vertical, and it reads line 1. Ask about 30 degrees, it reads line 2. The particle looks random to you because you never get to see the manifest. Flip through enough couriers and the answers scatter, the way a shuffled deck looks like chaos to someone who did not watch the shuffle. Now add the twin. Two particles fly apart. Quantum mechanics says that when you point both magnets the same way, the answers match perfectly, every single time, with no exceptions. That perfect agreement is the whole reason Einstein smelled a hidden code. Perfect agreement across a room, or across a galaxy, has an obvious explanation. The two couriers carry identical manifests. They were printed together. So far, nothing here is mystical. Nothing here is even hard. This is how coordination works everywhere else in the world. Three quiet ideas hold it together, and every one of them feels like plain common sense. First, the answers are real. They exist inside the particle before anyone asks. The moon is out there whether you glance up or not. Second, the particles are separate. What you do in your lab has no effect on the twin flying the other way. Influence takes time. Influence travels. Nothing outruns light. Third, you get to choose. Which angle you pick is up to you, or up to a coin, or up to a machine. Your choice is not secretly tied to what the particles are carrying. Realism, locality, freedom. Write those three on a wall, and you have Einstein's worldview in full. It is the worldview of every engineer, every mechanic, every person who has ever fixed anything. Things have properties. Distance protects you. Choices are choices. Any theory built on those three is called a local hidden variable theory. It is the most reasonable idea any human being has ever had about how the world runs underneath. And every experiment in this entire story exists to strangle it. Because those three innocent sentences, taken together, quietly make a promise about what the numbers coming out of your detectors are allowed to do. For 30 years, nobody noticed the promise was there. A physicist in 1950 who wanted to think about this question had a very simple career choice. Do not. The strangest thing about the Einstein and Bohr fight was how completely it stopped mattering. Two of the sharpest minds alive disagreed about the deepest structure of reality, and the disagreement produced no consequences whatsoever. Feed the same experiment through Einstein's picture and Bohr's picture, and identical numbers came out the other side. Same clicks, same flashes, same measurements. When two ideas predict exactly the same world, physics has a name for the gap between them: philosophy. And philosophy, in the middle of the 20th century, was something you did after retirement. The timing made it worse. Quantum mechanics was busy conquering everything. It explained why some materials conduct and others insulate. It cracked the chemical bond. It built the transistor, and the transistor built the modern world. Then came the laser, then nuclear physics, and everything that came with it. The theory was a machine that printed money and power. Nobody stops a working machine to ask what it means. A whole generation absorbed a working rule. Use the equations, get the answer, do not ask what is underneath. Anyone who kept asking was seen as soft, mystical, or finished. Graduate students learned to keep the question to themselves. Careers died over it. So the deepest question in physics sat in a drawer for 3 decades while the field got rich. But one man in 1951 did something small that mattered enormously, and he did it almost by accident. David Bohm was writing a textbook. He came to the Einstein argument and found it clumsy. The original 1935 version used position and momentum, quantities that flow continuously, which made the whole thing slippery and hard to picture. Bohm rebuilt it. He swapped the continuous quantities for spin. 2 particles, flying apart, each one spinning. Ask each one a yes or no question. Up or down, match or mismatch. Suddenly the abstract argument had the shape of something you could actually build on a table. 2 detectors, 2 dials, a pile of clicks. Bohm had turned a philosophical dispute into a machine sketch, and he did it inside a chapter of a teaching text without ever calling it a discovery. Almost nobody noticed. Einstein read it and liked it. Then Bohm's life detonated for reasons that had nothing to do with physics. He was hauled in front of a congressional committee during the American Communist Panic, refused to name colleagues, got arrested, got acquitted, and got quietly dropped by Princeton anyway. He left the country and finished his career in Brazil, then Israel, then London. Physics had shoved its most dangerous question into an exile's suitcase, and the exile kept working on it. Meanwhile, one more thing sat in the background, radiating false confidence over the entire field. A famous proof, a mathematical argument, published by one of the most brilliant men of the century, that appeared to demonstrate that hidden variables were flatly impossible. Not unlikely, impossible, ruled out by mathematics itself. That proof was why almost nobody bothered. Why chase something a genius already killed? The proof stood for 32 years, quoted in textbooks, taught to students, treated as settled fact. It was wrong. And the person who first spotted the error had already published the correction, in German 2 years before the Second World War. Nobody read it. John von Neumann could do almost anything with mathematics, and in 1932 he did something the field would regret for a generation. He published a proof. Hidden variables, he argued, are mathematically impossible. No theory of the kind Einstein wanted could ever reproduce the predictions of quantum mechanics. Case closed by pure logic before any experiment ever ran. Coming from him, this landed like a verdict from a mountaintop. He was the man who could outcalculate rooms full of professionals in his head. When von Neumann said a thing was impossible, you moved on. Physics moved on. The proof rested on an assumption buried deep in the machinery, phrased so technically that most readers slid right past it. In plain language, von Neumann assumed that a hidden variable theory would have to combine its answers in the same tidy way quantum mechanics does. If you measure quantity A and you measure quantity B, then the average of A plus B must equal the average of A plus the average of B. That sounds harmless. For averages over many runs, it is even true. For individual particles, it is a demand nobody had any right to make. Think about what he had done. He set out to test whether the universe might have a hidden layer with different rules, and then he required that hidden layer to obey the rules of the surface. He built a cage, checked whether anything outside the cage could fit inside, and announced that nothing outside existed. A 23-year-old mathematician saw it almost immediately. Her name was Greta Hermann. She had trained under Emmy Noether, one of the finest mathematical minds who ever lived, and she was not intimidated by reputations. In 1935, the same year Einstein was writing his 4 pages, Hermann published a paper identifying the flawed assumption precisely and explaining why it made the whole argument circular. She was correct. She was also a young woman, publishing in a philosophy journal in Germany in 1935. Her paper vanished without a ripple. It would sit unread for decades. So the false proof kept working. It sat in textbooks and lecture halls, a locked door with no wall around it, and for 32 years almost every physicist alive walked up to it and turned around. Then came 1952. David Bohm, still in the wreckage of his career, sat down and did the thing that was supposed to be impossible. He built a hidden variable theory, a complete one. Particles with definite positions at all times, guided along by a wave, every outcome fixed in advance by the starting conditions. It reproduced every prediction of quantum mechanics. Exactly. All of them. The thing von Neumann proved could not exist was now sitting on paper, working perfectly. Something in the mountaintop verdict was broken, and the field mostly responded by getting annoyed. Bohm's theory was called ugly, pointless, a step backward. Very few people asked the obvious question. One man did. He was a young Irish physicist working on particle accelerators, and Bohm's paper hit him like a slap. He later said it plainly. The impossible had been done, so what exactly had von Neumann proved? He went and read the original proof. He found the assumption. He saw the circle, and then he asked the question that would crack the universe open. If a hidden code is possible after all, is there anything it can never do? John Stuart Bell grew up poor in Belfast, in a house where he was the only child who stayed in school past 14. His family could not afford much. He got a job as a lab technician at Queen's University at 16, sweeping up and setting equipment, and the physicists there liked him enough to lend him textbooks. He read them all. He got into the university. He finished with top marks and went on to build a career designing particle accelerators. That was his day job. He was very good at it. He spent his working hours at the European Laboratory near Geneva, calculating how to steer beams of protons around a ring. The other thing, the question that actually gripped him, he did in his spare time. He called it his hobby. He was careful about who he mentioned it to. Bell had one quality that made him dangerous. He refused to be impressed. When everybody agreed on something, he wanted to see the argument himself, and if the argument was weak, he said so, in a soft accent with total calm. He had read von Neumann in the original German. He had found the rotten assumption. He wrote later that the proof was silly, and that once you saw the flaw, it fell apart in seconds. But knocking down a bad proof leaves you with nothing built. Bohm had shown a hidden code was possible. Bohm had also paid a terrible price for it, and Bell saw exactly what the price was. In Bohm's theory, the two twin particles stay connected. Move a detector in one lab, and the particle in the other lab feels it, instantly, across any distance. Bohm had bought realism by surrendering locality. He had built Einstein's machine using precisely the spooky action Einstein hated most. Bell stared at that trade and started to wonder whether it was a coincidence. Bohm needed the instant connection. Did every hidden variable theory need it? Was the spookiness optional, or was it the toll for entry? In 1964, on sabbatical in America, Bell sat down and answered his own question. He did not build a theory. He did something far more clever and far more brutal. He wrote down the 3 assumptions from Einstein's worldview. The answers are real, the labs are separate, the choices are free. Then he asked what those 3 assumptions, all by themselves, forced the experimental numbers to do. He did not pick a specific hidden code. He allowed every possible hidden code, simple ones, monstrous ones, codes with 1 trillion lines, codes nobody had thought of yet. Any instruction sheet at all, so long as it respected those 3 sentences. Then he found the boundary. He proved that every theory in that entire infinite family without exception has a ceiling. Run the experiment, count the matches, combine the counts in a specific way, and the total can never climb above a certain number. Not sometimes. Never. It was a fence around the whole territory. Every possible hidden code, no matter how clever, lives inside the fence. Then Bell worked out what quantum mechanics predicts for the same measurement. The number came out higher. Quantum mechanics predicts a value that sits outside the fence, comfortably outside, far enough that no experimental sloppiness could explain it away. Which meant the 30-year stalemate was over. Einstein's picture and Bohr's picture disagree about something a machine can count. The paper was 8 pages long. Bell sent it to an obscure journal that paid its authors, and it was so obscure that the journal folded shortly after. For 5 years, almost nobody read the most important paper in the history of quantum physics, and the fence Bell built has a shape you can understand without a single equation. Forget particles for a moment. Picture a dating show with a very strange rule. 3 questions sit in sealed cards. Do you like coffee? Do you like dogs? Do you like winter? Every contestant walks in having already decided their answers. Yes or no. Locked in. No changing. Now 2 contestants come from the same town, raised the same way, and they always answer identically. Ask them both about coffee, they match. Ask them both about dogs, they match. Every time, no exceptions. Here is the game. You put them in separate rooms. You ask each one a single question, chosen at random from the 3. Then you compare. Sometimes you ask both the same question. They match, obviously. The interesting runs are when you ask different questions. Coffee to one, dogs to the other. Winter to one, coffee to the other. Now count the disagreements. Every contestant walks in as one of only 8 possible types. Yes, 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 no, yes, no, yes. All the way down to no, no, no. That is the whole menu. Every human being with 3 locked answers is one of those 8. Look at any single type and count how often 2 different questions disagree. Take yes, yes, no. Coffee against dogs, both yes, agreement. Coffee against winter, yes against no, disagreement. Dogs against winter, yes against no, disagreement. 2 disagreements out of 3 pairings. Take yes, yes, yes. Every pairing agrees. 0 disagreements. Try all 8 types. Something rigid appears. The disagreement count is always 0, or always 2/3. Never anything else. It cannot be anything else, because 3 yes or no answers do not have enough room to be more contrary than that. So across a long run of contestants, mixed however you like, the fraction of disagreements has a ceiling. It can never exceed 2/3. Ever. That ceiling is a Bell inequality. Look at what just happened, because it is the most underrated move in physics. Nobody specified what the contestants were thinking. Nobody described their personalities, their childhoods, their reasoning. The ceiling came from one fact alone. The answers existed before the question arrived. That is the entire trick. Bell found a number that every possible instruction sheet must respect, without ever needing to read a single sheet. Now swap the contestants for particles. Swap the 3 questions for 3 angles of a magnet. Swap yes and no for spin up and spin down. Send the twins into separate labs. Pick an angle at random for each. Count the disagreements. Einstein's world says the twins arrive with their answers packed, so the ceiling holds. 2/3, a hard wall guaranteed by arithmetic, so plain a child could check it. Quantum mechanics says something else entirely. Bell ran the calculation for those same 3 angles and found the theory predicts a disagreement rate of 3/4. 3/4 sits above 2/3. Sit with the size of that. The gap is small enough to seem petty, and it is the widest crack in the history of science. A gap of that size means no instruction sheet exists. Not a clever one, not a complicated one, not one written by a god. The particles cannot be carrying their answers, because carrying answers forces a number, and nature refuses to produce that number. Bell had converted the deepest question about reality into counting clicks and dividing. There was one small problem left. In 1964, nobody on Earth could actually run it. The strangest part of Bell's result is the direction the numbers break. Everybody expects quantum mechanics to be the messy one. Fuzzy, uncertain, random, blurred. Einstein's hidden code sounds like the tidy option, the one where everything lines up because everything was planned. Reverse that instinct completely. Quantum particles are the ones that agree too well. Watch the twins as you slowly turn one detector. Point both magnets straight up. The twins match, every time, perfectly. Both worldviews say the same thing here. Now tilt one magnet by a small angle. Mismatches begin appearing. A few at first, more as you tilt further. Keep going until the 2 magnets sit at right angles, and the twins have collapsed into pure coin flipping, matching half the time. Both pictures agree at the endpoints. The fight is over the middle. Einstein's code says the mismatch rate climbs like a ramp. Straight, steady, honest. Double the tilt, double the disagreement. The instruction sheets are fixed, so tilting your magnet simply reads a different line, and lines are independent of each other. Errors accumulate the way rain fills a bucket, one drop at a time. Quantum mechanics says the mismatch rate climbs like a curve, slow at small angles, lazy, reluctant. The twins cling to each other much harder than any ramp allows, and then the curve steepens and catches up at the far end. That laziness at small angles is the entire crime. Here is a comparison that makes it visible. 2 archers stand at opposite ends of a field, shooting at their own targets, and their arrows always land in matching spots. You explain it easily. They memorize the same pattern before they walked out. Now nudge one archer's target by 1 degree. His arrow should drift by 1 degree of error, independently of his partner. Instead, his arrows stay glued to hers. Nudge again, still glued. The 2 shots track each other more tightly than 2 memorized patterns are permitted to track. Somewhere, the twins are cheating. Add up the mismatches across several angles the way Bell prescribed, and Einstein's ramp always lands at or below the fence. Quantum mechanics vaults over it by roughly 40%. Physicists write this as a single number. Einstein's world caps out at 2. Quantum mechanics reaches 2.82 and change. 2.82 is what the universe scores on a test that the universe is supposed to fail. There is one more twist that keeps people up at night. Quantum mechanics does not go as high as it could. Pure mathematics allows correlations all the way up to 4, and those stronger correlations still refuse to send any usable signal faster than light. So nothing in relativity forbids them. Nature stops at 2.82 anyway, above the fence, below the ceiling, parked at a value nobody has fully explained. The universe cheats, and it cheats by a precise, disciplined, unexplained amount. All of this was arithmetic on a page in 1964. Bell had written the test. Nobody had the machine. Producing twin particles reliably, aiming detectors that switched fast enough, counting clicks with enough precision to see 40%, all of it sat beyond the equipment of the era. 5 years passed. The paper sat in a dead journal. Then a graduate student in California pulled it off a library shelf, read it, and decided to use it to prove Einstein right. John Clauser was a graduate student in New York with a problem. He believed something everybody around him considered crackpot. He thought quantum mechanics was wrong. He had found Bell's paper on a library shelf in 1967, 3 years after publication, sitting untouched. Reading it, he understood immediately that the 8 pages contained a machine sketch, and that nobody had built the machine. He asked his advisors for permission to build it. The answers ranged from discouraging to hostile. One senior physicist told him he would destroy his career. Testing quantum mechanics was seen as testing gravity by jumping off a chair. The theory had survived 40 years of everything the world could throw at it. Clauser did it anyway, because he was certain the fence would hold. He was so confident that he made a bet with a colleague. Real money on Einstein. First, he needed a sharper version of the test. Bell's original required perfect matching at identical angles, and no real machine is perfect. Clauser teamed with 3 others and rewrote the inequality into a form that tolerated imperfection, a version any messy laboratory could actually use. It became the workhorse for every experiment that followed. Then he moved to Berkeley and started scrounging. The apparatus he assembled would embarrass a modern lab. He heated calcium atoms in a vacuum until they glowed. Calcium has a useful habit: excite it correctly, and an atom drops through 2 energy steps in a row, spitting out 2 photons in opposite directions, born from the same event, linked in polarization, twins manufactured by the millions in a hot vapor. On either side, he built polarizing filters out of stacks of glass plates, 10 feet long, each stack weighing more than a person. Behind them sat photomultiplier tubes to catch the light. He rotated the filters by hand. He scavenged parts. He worked with a graduate student named Stuart Friedman, and the 2 of them ran the machine for 200 hours to gather enough clicks to say anything at all. The photons were feeble. The filters were crude. Most of the light escaped uncaught. Every click was precious. In 1972, the numbers came in. The universe scored above the fence. Clauser refused to believe it. He assumed he had broken something. He tore the apparatus down and rebuilt sections, hunting for the mistake he was sure he had made. He checked the alignment, he checked the electronics, he checked everything. The number stayed above the fence, 6 standard deviations above, which in the language of experiments means the odds of an accident are worse than 1 in 100 million. Clauser had set out to rescue Einstein's universe, spent years of his life on it, and delivered the first hard evidence that it does not exist. He paid his bet. He said afterward that he was very unhappy about the result. He kept looking for the flaw for years. And here is the thing. He was right to keep looking. His own experiment had holes in it, and he knew exactly where they were better than anyone alive. Most of the twins his machine created were never caught at all. That gap would take another 43 years to close, and it gave the hidden code a place to hide that was far more powerful than anyone first realized. A young French physicist walked into John Bell's office in 1975 and announced he wanted to build a better version of the test. Bell's first question was blunt. "Do you have a permanent position?" Alain Aspect said yes. Bell relaxed. The question was serious. Anyone without job security who touched this subject was gambling with their future, and Bell knew it because he had spent a decade hiding the work himself. Aspect had spotted the weakness in Clauser's machine, and it was a beauty. Think about what a fixed filter really means. Clauser set his polarizers by hand, then walked away, then ran the experiment for hours, which means the filters were sitting at their chosen angles long before any photon left the calcium atom. Long before. Hours before. So imagine a hidden code that is sneakier than the simple version. The twins are born inside the apparatus. The filter angles are already set. Light from those filters, or any other influence, has ages to reach the source. Plenty of time for the particles to learn the settings and cook up an answer that mimics quantum mechanics perfectly. That escape route is worthless as physics and airtight as an excuse. To close it, you must choose the angles after the photons are already flying, and choose them so late that no signal travelling at light speed could carry the news to the other side in time. You have to beat light across a room. Aspect worked the numbers. His photons would fly about 20 feet from source to detector, taking roughly 40 billionths of a second. So his switch had to change its mind in less time than that. Mechanically impossible. Nothing built from moving parts operates on that scale. He used sound. He built a small cell of liquid and drove a standing sound wave through it, vibrating millions of times per second. The wave squeezed the liquid into layers of alternating density, turning it into a diffraction grating that appeared and vanished as the sound cycled. A photon entering during one phase sailed straight through toward one polarizer. A photon entering during the opposite phase got deflected toward another polarizer with a different angle. The switch had no moving parts and flipped every 10 billionths of a second. Picture a railway junction that changes tracks faster than any train can send a warning ahead, so no engine can ever know which way it will be sent. Two of these cells, one on each side, running independently, throwing photons at 4 different polarizer settings, 12 meters apart. By the time the switch made its choice, the twin on the far side was already in flight and could receive no word about it. In 1982, Aspect ran it. The score came in at 2.7, against a fence at 2. 5 standard deviations clear. The universe cheated again, and this time it cheated with the settings chosen mid-flight. Aspect's result went around the world. It was the moment the question stopped being embarrassing and became merely difficult. Bell was delighted, and Bell was also honest. He pointed out that the switching was driven by a periodic sound wave, which is predictable rather than random. A truly determined hidden code could in principle anticipate a repeating rhythm. And Bell knew about a second hole, a far worse one, sitting in the heart of every optical experiment ever run, including Aspect's. The machines were only catching a tiny fraction of the photons they made. Suppose you want to know the average height of a country, and you only measure people who can reach the top shelf. Every optical Bell test for 30 years had that problem. The detectors of the era were dreadful. A photomultiplier tube in the 1970s caught perhaps 5 photons out of every 100 that hit it. The rest passed through, absorbed, wasted, gone. Add lossy filters and imperfect optics and the real numbers got worse. In some early runs, fewer than 1 twin pair in 1,000 produced clicks on both sides. So every experimenter made an assumption. They called it fair sampling. The photons we catch, they said, are a random sample of the photons we make. Whatever the caught ones do, the missed ones would have done too. Sounds reasonable. It is also completely unprovable, and it hands the hidden code a weapon. Picture a rigged election. You do not need to change a single vote. You only need to control who makes it to the polling station. Now give the particles that power. Suppose every twin carries an instruction sheet with an extra line on it. A line that says something like, if the filter is set near this angle, do not trigger the detector. Stay quiet. Vanish. The particles that show up produce a beautiful violation of Bell's fence. The particles that stay silent get thrown away as detector inefficiency, which everyone expects anyway, because the detectors really are terrible. The sample selects itself, and the selection does the cheating. Physicists worked out exactly how good detectors need to be before this escape route closes. For the standard setup, the threshold sits near 83%. Below that, a hidden code with a hiding instruction can fake any result you like. Above it, the trick stops working, because too many particles are being seen for the silent ones to swing the outcome. 83% when the state of the art was 5. This is the detection loophole, and it was not a philosopher's quibble. Real theorists built real hidden variable models that reproduced Aspect's exact data using nothing but the missing photons. The models were ugly. They worked. For decades, everyone knew the hole was there, and nobody could fix it, because the fix required detectors that did not exist. Then, in 2001, a team at a standards laboratory in Colorado tried something completely different. Forget photons, use ions. They trapped 2 beryllium ions with electric fields and entangled them. Ions have a wonderful property. When you measure one, it either fluoresces brightly or stays dark, and you catch essentially every single event. Detection efficiency near 100%. They ran the test. The universe cheated with no missing particles to blame. The detection loophole was closed, and in closing it, they had blown the other one wide open. Their 2 ions sat 3 micrometers apart, 3 millionths of a meter. A human hair is 30 times thicker. At that distance, light crosses the gap in a time so short that no switch on Earth could beat it. Anything happening at one ion could have whispered to the other 1,000,000 times over before the measurement finished. So now physics had 2 experiments and a maddening trade. Close the distance and the particles can talk. Open the distance and the particles can hide. Every experiment on Earth had one door bolted and the other swinging open. Somebody was going to have to shut both at once. The locality loophole has a beautiful, terrible simplicity. If a message could get there, you have proved nothing. Aspect had attacked it with sound waves and 12 meters. 16 years later, a group in Innsbruck did it properly. Gregor Weiss, working under Anton Zeilinger, ran optical fiber across a university campus and separated his 2 detector stations by 400 meters. He built each station its own random number generator, driven by a noisy physical process, making fresh, unpredictable choices for every single photon. 400 meters buys you about 1 1/3 microseconds of light travel time. That is an eternity in electronics. Weiss had time to make the choice, apply it, complete the measurement, and record the result, all before any signal from the other station could possibly arrive. Each station also had its own atomic clock and its own local computer, so the 2 sides had no communication of any kind during a run. They compared data afterward. The universe cheated by 30 standard deviations. The locality loophole was closed, cleanly, with the timing verified to the nanosecond. And the detection loophole yawned open, because Weiss was using photons, and photons in 1998 got caught about 5% of the time. Here is the maddening shape of the problem. The 2 holes pull in opposite directions. To close locality, you need distance. To get distance, you need particles that travel, which means photons. Photons are hard to catch. To close detection, you need particles you can hold still and interrogate carefully. Atoms, ions, superconducting circuits, things you can trap, and things you can trap sit in a box next to another box, close enough for light to cross the gap in a heartbeat. Fast and slippery, or captured and cramped. Pick one. For 14 years, everybody picked one. The situation had a strange psychological effect on the field. Almost nobody seriously believed a hidden code was exploiting the gaps. The models required to do it were baroque, contrived, and looked like a lawyer's argument rather than a description of nature. Believing them meant believing the universe was actively conspiring to trick us. But physics does not run on what people believe. Bell's whole achievement was replacing belief with counting. Leaving a loophole open meant the counting was incomplete, and incomplete counting is exactly what everyone spent 3 decades escaping. So a small, stubborn community kept grinding at the engineering problem. 2 technologies had to arrive. The first was detectors that actually work. Superconducting nanowires, cooled to a fraction of a degree above absolute zero, so cold that a single photon striking the wire deposits enough energy to break the superconductivity and produce a measurable pulse. These catch more than 90% of what hits them. They pushed past the 83% threshold with room to spare. The second idea was stranger. If you cannot catch all your particles, you can stop trying, and instead arrange to know in advance which runs will succeed. The trick is called entanglement swapping, and it works like a wedding officiated by a stranger. 2 distant objects each fire a photon toward a station in the middle. The 2 photons meet and get measured together, in a way that reveals nothing about either one alone. When that middle measurement gives a specific result, the 2 distant objects become entangled, and the station rings a bell announcing it. The photons can fail, the photons can vanish. Whenever they do, no bell rings, and no trial counts. The trial only exists once you already know the entanglement is there. In 2015, a group in a Dutch city built exactly that. out of diamonds. Ronald Hansen's team spent years failing at something that had to work perfectly or not at all. Their setup ran across the campus of a technical university in the Netherlands. 2 laboratories, separated by 1 3/10 kilometres, roughly 8/10 of a mile. Far enough that light needs 4 1/3 microseconds to cross. In each lab sat a diamond. Diamonds are carbon crystals, and no crystal is perfect. Occasionally a carbon atom goes missing and a nitrogen atom sits beside the hole. This floor is called a nitrogen vacancy center, and it behaves like a single trapped electron with a spin you can control with microwaves and read with laser light. It is a natural quantum bit, sitting inside a rock, stable at temperatures far friendlier than most quantum hardware demands. Each diamond held 1 such floor, 2 electrons a mile apart, inside 2 stones. Each electron was made to emit a photon whose colour and timing tied it to the electron's spin. Both photons then raced down optical fibre to a third building, sitting roughly in the middle, where they met on a beam splitter. The middle station performed a measurement that could not tell which photon came from which lab. That ignorance is the whole engine. By destroying the information about origin, the measurement stitches the 2 distant electrons into a single entangled pair. When it worked, the station announced it. That announcement is what made the experiment airtight. Every trial was declared valid before either lab looked at its electron. The electrons themselves were then measured with efficiency near perfect, because reading a spin inside a diamond gives an answer essentially every time. Detection loophole, closed by the diamonds. Locality loophole, closed by the mile. The timing was choreographed to the nanosecond. Each lab used a fast random number generator to pick its measurement angle after the announcement, then completed the measurement before any signal from the other lab could arrive. The whole sequence had to fit inside 4 microseconds, and it did. Now, the price. The photons almost never made it. Fibre absorbs light. Beam splitters are fussy. The success rate for a swap was so brutal that the machine produced on average a few valid trials per hour. The team ran the experiment for 18 days and collected 245 valid trials. 245. A modern optical experiment gathers millions in a minute. Hansen's team spent nearly 3 weeks to gather fewer events than there are seats in a small cinema. And with 245 trials, the universe scored above the fence. The statistics were thin, and they were honest about it. The chance of a fluke came out at about 4%, weak by physics standards, suggestive rather than crushing. Then 2 other groups, one in Colorado and one in Vienna, finished their own loophole-free tests within months using the new superconducting nanowire detectors and millions of photon pairs. Their odds against a fluke ran to 1 in 10 million and beyond. 3 independent machines, 3 different technologies, both loopholes shut. Same verdict. Einstein's universe had been executed 3 times in 1 year. But loopholes have a nasty habit. Close 2, and the survivors noticed the 3rd. Because every one of these experiments still trusted one thing it had no way to prove. A machine at a Swiss university took Bell's question and asked it 1,000,000 times before lunch. The Hansen diamond test proved the point, and proved it slowly. 245 trials in 18 days is a triumph and an agony. Physicists wanted the same rigour with volume, because volume is what turns a suggestive result into a fact carved in the stone. In 2023, a team led by Simon Storz at a Zurich institute did it with superconducting circuits. These are the same devices that sit inside the quantum computers making headlines. Tiny loops of metal, printed on a chip, cooled until the metal loses all electrical resistance. Send current around such a loop and it can circulate both ways at once. That is the quantum bit. Superconducting circuits have a wonderful advantage. They are fast, loud, and easy to read. Measuring one takes under 100 nanoseconds and gives an answer almost every time. Detection efficiency is a solved problem. They also have a crippling disadvantage. They only function near absolute zero, at a few thousandths of a degree above the coldest temperature that exists. So they live inside refrigerators the size of a phone booth, and refrigerators sit in rooms, and rooms are small. To close the locality loophole, the team needed real distance between the chips. So they built a tunnel, a 30-metre aluminum tube running through the basement corridor between 2 laboratories, holding a waveguide that carries microwave photons between the chips. and because those photons would be destroyed instantly by heat, the entire 30-meter tube had to be refrigerated along its whole length to about 50 thousandths of a degree above absolute zero. Picture a 100-foot pipe held colder than the emptiness between the stars running under a hallway, so that two chips could exchange a whisper of microwave light without a single stray heat, ripple corrupting the message. The cooling took weeks. The tube weighed 1 1/3 tons. 30 meters gives about 100 nanoseconds of light travel time, so the team had 100 nanoseconds to generate a random setting, apply it, complete the measurement, and record it. They engineered every step down to the nanosecond and made it fit. Then they ran it. Over 1 million trials, in roughly 20 minutes, the universe scored above the fence. The odds against a statistical accident came out so small that writing them requires a number with more than 100 zeros after it. For comparison, the number of atoms in every star in the observable universe has about 80 zeros. Both loopholes shut. Statistics past the point of absurdity. A completely different physical system from diamonds, photons, or ions. And here is what makes this experiment sting in a way the earlier ones do not. Those chips are not exotic prototypes built for a philosophy question. They are the working parts of the machines that companies are selling. The refrigerators, the microwave lines, the readout electronics, all of it is industrial hardware now. Bell's fence, the one that decides whether reality has a hidden instruction sheet, has become a routine calibration check inside a quantum computer. The most profound question ever asked about the nature of existence is now something engineers verify to make sure the equipment is working. There is only one hole left in the whole edifice. It is the oldest one. It is the one Bell himself worried about most, and it is the one that no machine, no matter how cold or how fast, can ever fully close. It has to do with who is choosing. Every Bell test ever run rests on one assumption that no experiment can prove, that the setting was free. Look at the structure of the whole argument. Twins fly apart, you pick an angle for your detector, your partner picks an angle for hers. You compare. If the numbers break the fence, no instruction sheet exists. The proof requires that the angles were picked independently of the twins, that the choice and the particles share no common source. Bell called this measurement independence, and he treated it as so obvious that his original paper barely paused on it. Now attack it. Suppose the choice is not independent. Suppose something in the past nudged the random number generator and the particle source together. The generator would look random. Every statistical test would pass. And underneath, quietly, the settings you picked would be correlated with the instruction sheets the twins carry. If that happens, Bell's proof collapses entirely. Not weakens, collapses. A hidden code that knows in advance which angles you will select can reproduce every result ever measured, using nothing but ordinary local physics, with no spooky action anywhere. The mathematics on this is brutal. Theorists have calculated how much correlation you would need. The answer is shockingly little. A hidden code that gets a small nudge, a few % of influence over your choice, can fake the entire quantum world. This is the freedom of choice loophole, and it has a quality the others lack. You cannot engineer it away. There is no colder tube, no faster switch, no better detector that fixes it. Because whatever you use to make your choice is a physical object. A quantum random number generator sits in a room. A chip has a history. Every atom in it came from somewhere, and that somewhere connects, eventually backward in time to a shared past. Trace any two objects on Earth back far enough and their light cones overlap. Everything in this room, everything in the next room, everything in the laboratory shares a common history reaching back to the beginning. So the question becomes brutally concrete. How far back do you have to go before the conspiracy has to start? If the random number generator was built last year, then anything from before last year could have set up the correlation. That is a lot of universe to hide a conspiracy in. Push it back. Use a generator that makes its choice in nanoseconds, and the correlation only needs to be arranged nanoseconds earlier, in the light cone reaching back from that moment, which still includes the whole planet, the whole solar system, and every star whose light has reached us. You can never eliminate the shared past. The Big Bang is a shared past for everything. What you can do is push the conspiracy backward, make the hidden code commit earlier and earlier, force it to have arranged the fix further and further in the distance, until believing in it means believing the universe was rigged before the Earth existed. You cannot close this loophole, you can only make it embarrassing. And to do that, you need a source of choices that has nothing to do with your laboratory. Something with a history so ancient and so remote that any conspiracy linking it to your photon source would have to have been arranged in the deep past. You need to stop asking machines to choose. You need to ask the sky. In April of 2016, a team in Vienna pointed 2 telescopes at 2 stars and let the stars run their experiment. The idea belongs to a small group that included Anton Zeilinger and a cosmologist from Boston, and once you hear it, it is hard to believe nobody built it sooner. Stop using a random number generator. Use ancient light. Here is the machine. A source in a Vienna building makes entangled photon pairs and fires them toward 2 detector stations about 1 kilometer apart. Each station has a small telescope beside it, aimed at a specific star. Photons from that star pour down into the telescope. A filter sorts them by colour. Redder than a threshold, the setting flips one way. Bluer, it flips the other. Each arriving starlight photon sets the angle for the next lab photon in real time within microseconds. The choices are made by a light that has been travelling since before anyone alive was born. One telescope watched a star roughly 600 light-years away. The other watched a star about 1900 light-years away. So one setting was decided by a photon that left its star around the time the Roman Empire was collapsing, and the other by a photon that left before the empire existed at all. Think about what that does to any conspiracy. For a hidden code to rig this experiment, the correlation between the star and the photon source in Vienna would have to have been established before that starlight was emitted. The last chance to arrange it was 600 years ago. The plot has to predate the printing press. Every plotter within that window is exonerated. The entire recent history of the universe, all 600 years of it, is now off the table. The team ran the experiment. The universe scored above the fence hard by nearly 12 standard deviations. The technical challenge was ugly in ways nobody anticipates. Starlight is faint. City sky glows. Vienna is full of streetlights, and stray photons from a lamp or the moon would poison the setting choices with local light, reopening exactly the hole they were closing. So they filtered aggressively, aimed precisely, and characterized their background sources down to the percent. They calculated how many of their setting photons were genuinely from the star, and how many were local contamination, and they built that number into the analysis honestly, so the claim survived the contamination rather than pretending it away. They also had to prove the starlight itself was random. A star's colour at any instant fluctuates for many reasons, and the fluctuations are unpredictable in practice. The team tested their bit streams against a battery of statistical checks and found no pattern. Then they published and immediately went hunting for something older. 600 years is a beautiful result, and a small fraction of cosmic history. The universe has been running for nearly 14 billion years. Pushing the conspiracy back 6 centuries removes a slice so thin it barely registers on the timeline. 99.9999% of the past was still available to the plot. They wanted to erase almost all of it. For that, a star is far too close. They needed light that had been travelling since before the sun existed, since before the Earth had a surface, since a time when the galaxy itself was still assembling. They needed the brightest objects in the universe. On a mountaintop in the Canary Islands, 2 enormous telescopes turned toward 2 dead engines at the edge of the observable universe. This was January of 2018, and the team had traded the small Vienna telescopes for a pair of 4-meter giants at an observatory perched above the clouds on La Palma. They needed the collecting area, because what they wanted to catch was almost unimaginably faint. Quasars. A quasar is a supermassive black hole in the centre of a young galaxy, feeding. Matter spirals in, compresses, heats and blazes. A single quasar can outshine an entire galaxy of hundreds of billions of stars, all from a region smaller than our solar system. They were common in the early universe and are almost extinct now. So every quasar you can see is a window into the deep past, because the light left before the engines shut down. The team picked 2 of them, on opposite sides of the sky. One telescope caught light emitted 7.8 billion years ago. The other caught light emitted 12.2 billion years ago. Sit with the second number, 12.2 billion years. That photon left its quasar when the universe was a little over 1 billion years old. It has been in flight ever since. Our sun did not exist. The Earth did not exist. The atoms that would become your body were still inside stars that had not yet been born. That photon crossed the void for 12 billion years, entered a 4-meter mirror on a Spanish mountain, and its colour decided the angle of a polarizer. The photons from these quasars arrived at a trickle. The system had to make a setting choice for every entangled pair, and quasar photons were too scarce to supply one each. So the team used the quasar bits to set the angle, and held each setting until the next quasar photon arrived, feeding a fresh cosmic decision into the machine as fast as the universe delivered them. The universe scored above the fence by 9.3 standard deviations. The odds of a fluke came out around 1 in 100 million trillion, and then they calculated the thing that makes this experiment immortal. Given where those quasars sit, given the geometry of the sky, given how the universe has expanded since the beginning, they worked out how much of cosmic history could still contain a conspiracy. The answer was 4%. 96% of the entire space-time volume of our past, stretching from the Big Bang to the present moment, has been eliminated as a place where a local hidden code could have arranged the fix. Read that again slowly. A group of people used dead black holes to rule out 96% of the history of everything. The remaining 4% sits crushed against the beginning, in the first sliver after the universe started before those quasars ignited. So the loophole survives, technically. A hidden code can still work if it was written into the initial conditions of the universe itself, if the correlation between what a black hole did 12 billion years ago and what happened in a Spanish laboratory in 2018 was baked in at the moment of creation. That is what remains of Einstein's idea. That is the last shelter, and a small number of physicists live there on purpose. But before we go to them, one more experiment tried the opposite tactic entirely. Instead of reaching for the oldest thing in the universe, it reached for the messiest. It asked 100,000 people to be random. On the 30th of November 2016, a video game asked strangers around the world to be unpredictable and used them to interrogate reality. The reasoning went like this. Every physical random number generator is an object with a history. Starlight and quasars push the conspiracy into the deep past. There is one other approach, and it is the one Bell himself used when he described the ideal experiment. He wrote about experimenters choosing settings, and he meant people. If human choices are free in any meaningful sense, then human choices are the cleanest setting generator available. So a consortium built a game. Players opened a website and were shown a stream of prompts. Press 0 or 1. Keep pressing. Try to be unpredictable. A machine learning model watched each player and tried to predict their next button press, and the game scored you on how badly you beat it, because humans left alone are terrible at randomness and fall into patterns fast. The competition kept them sharp. Every bit produced went into a central system and was streamed live to laboratories across the planet. 12 laboratories, 5 continents, photons in Vienna, trapped atoms in Munich, superconducting circuits in China, optical fibers in Brisbane, single atoms in Barcelona and Rome and Nice and Conception and Shanghai. The bits arrived from human fingers and set the measurement angles in real time. They needed roughly 1,000 bits per second to keep every laboratory running. They got far more. Over 100,000 people participated. Across the day, the players generated more than 97 million bits. The whole thing ran for 12 hours, chasing daylight around the planet as different regions woke up. Every laboratory reported the same verdict. The universe scored above the fence. Now, be careful about what this proves, because the temptation to overreach here is enormous, and the team themselves were rigorous about it. Human choices are not proven random. Your brain is a physical object obeying physical law, and whether your button press is free in the deep sense is a question this experiment cannot answer. That was never the claim. The claim is narrower and still sharp. To fake this result, a hidden code would need to have influenced the specific button presses of 100,000 separate human beings, scattered across every populated continent, in a way precisely coordinated with the photon sources sitting in 12 different laboratories. The conspiracy now needs to reach into human nervous systems, all of them, simultaneously, correctly. Believing that costs something, not mathematically, because mathematically it still works. It costs something in credibility. Between the quasars and the crowd, the shape of the last surviving hidden code has become clear. It has to have been written at the beginning of time, and it has to reach forward across 14 billion years to coordinate black holes, laboratories, and the fingers of strangers playing a game on a Wednesday. In 2022, the Nobel Committee looked at all of it and made a decision. In October of 2022, a committee in Stockholm handed the world's most famous science prize to 3 men for settling an argument that physics had spent decades calling a waste of time. John Clauser was 79, Alain Aspect was 75, Anton Zeilinger was 77. The citation praised experiments with entangled photons, the violation of Bell inequalities, and the founding of quantum information science. Think about the career arc buried in that sentence. Clauser had been warned that this work would end him. He built his apparatus from scavenged parts, ran it for 200 hours, and got a result he spent years trying to disbelieve. Afterward, he struggled to find permanent work. He drifted between positions. For a long stretch, the most important experiment of his generation was something he had to explain away in job interviews. Aspect had been told to get a permanent position before touching the subject, and he took the advice seriously enough to secure one first. Zeilinger built his career on the machinery that grew out of the question. He teleported the quantum state of a photon in 1997. His group later sent entangled photons across 90 miles of open air between 2 Canary Islands. His former student went on to build a satellite that beams entangled photons to ground stations 1,000 miles apart. That last part is the reason the prize finally came. The committee did not honour philosophy. It honoured a technology. Because somewhere in the 1990s, physicists realised that the excess correlation Bell discovered is a resource. You can spend it. Quantum cryptography uses it. 2 parties share entangled particles and generate a key that cannot be intercepted without breaking the correlation, which the parties then detect. Quantum computing uses it as the raw material for its speed-ups. Certified random number generation uses a Bell violation as proof that a number was genuinely unpredictable rather than secretly rigged, because a machine that breaks the fence cannot have been running on a pre-written script. The question of whether the universe carries a hidden instruction sheet turned into a product you can buy. And this is exactly why the prize stings. Every physicist who told a student that these questions were career suicide was making a prediction about what matters. They predicted the question would stay barren forever. They were wrong by an entire industry. One name is missing from the citation, for the saddest possible reason. John Bell died on the 1st of October 1990 of a sudden brain hemorrhage. He was 62. He had been working at his laboratory near Geneva that week, healthy, active, with no warning of any kind. He was reportedly nominated for the Nobel Prize that same year. The prize is never awarded after death. Bell missed the honour for his own theorem by a matter of months, and by 32 years. He never saw the loophole-free tests. He never saw the diamonds a mile apart, or the quasar light picking the angles, or the 100,000 strangers pressing buttons. He also never softened. Late in his life, Bell said something that most people who quote him leave out. He said he hoped the experiments would fail. He wanted the fence to hold. He built the weapon that killed Einstein's universe, and he was rooting for Einstein the whole time. So what actually died in Stockholm? Less than almost everyone thinks. The victory speeches went too far, and the fine print is far more interesting than the headline. The popular summary of all this work is 1 sentence long, and it is wrong. People say the experiments proved that reality does not exist until you look. That is a bigger claim than any of these machines can support. Here is what actually died. Bell's proof needed 3 ingredients. The answers exist before you ask. The 2 labs cannot influence each other. Your choice of setting is unconnected to the particles. Combine all 3 and you get the fence. Nature jumps the fence. So at least one of those 3 ingredients is false. At least one. That is the entire logical content. The experiments say the trio cannot all stand together. They stay silent about which one falls. This is the difference between proving a defendant guilty and proving that at least one of 3 suspects is guilty. Enormous progress, very far from a conviction. Look at your options. You can drop the second ingredient, keep definite properties, and accept that a measurement here genuinely reaches out and shapes, Something there, instantly, at any distance. Reality stays solid, and the world becomes deeply connected. You can drop the first ingredient, say a particle carries no answer at all before the question arrives, and that the answer gets created in the moment of measurement. You can drop the third, say your choices were correlated with the particles all along, and the appearance of freedom is a very convincing illusion. Or you can do something stranger. Say that every outcome happens in separate branches, and that measurement never produces a single result at all. 4 exits, all open, all consistent with every experiment ever run. Physicists have loud personal preferences here, and the arguments get vicious. What they do not have is data that picks a winner. Now the fine print that makes the whole thing weirder. The instant connection, whatever it is, refuses to carry a message. Suppose you and a partner share entangled particles across the galaxy, and you want to send a warning. Measure yours, and your partner's particle snaps into a definite state instantly. You have influenced her particle. Everyone agrees on that. She learns nothing. Her results look like perfect coin flips no matter what you do. 50% up, 50% down, in every direction she checks. She sees random noise. She always sees random noise whether you measure or weight or throw your particle in a furnace. The correlation only appears when the two of you compare notes afterward, and comparing notes requires a phone call, and phone calls travel at light speed like everything else. Picture 2 people opening identical sealed envelopes, discovering the contents always match, and being completely unable to use that matching to say a word to each other. The pattern is only visible from outside, after both halves are on the same table. Physicists call this the no-signaling theorem, and it is why relativity survives untouched. Whatever is happening between entangled particles, it cannot deliver a single bit of usable information faster than light. The universe cheats, and the universe refuses to let you profit from the cheating. So the fields split into camps, each one sacrificing a different ingredient, each one insisting the others gave up the wrong thing. The oldest camp made the boldest trade. It kept everything Einstein wanted, and paid a price he would have found unbearable. There is a version of quantum mechanics where every particle has a definite position at every instant. Nothing is ever uncertain, and the entire universe runs like clockwork. It exists. It works. It reproduces every experimental result ever recorded, and almost nobody uses it. The idea arrived in 1927 at a conference in Brussels from a French aristocrat named Louis de Broglie. He proposed that a particle is a real object with a real position, riding on a wave that pushes it around. The wave tells the particle where to go. The particle goes. He presented it. He got shredded in the discussion. He abandoned it and adopted the standard view for the next 25 years. David Bohm rebuilt it from scratch in 1952, without knowing de Broglie had gotten there first. Here is the whole machine. An electron is a tiny thing at a specific place. Alongside it, filling space, sits a wave. The wave spreads out, passes through both slits, interferes with itself. The electron rides one path and gets steered by the shape of the wave around it. Fire electrons one at a time at a double slit, and each one goes through a single slit, like a sensible object. But the wave goes through both. The wave interferes. The interference reshapes the wave's landscape. The landscape steers the electron toward bright bands and away from dark ones. Interference pattern, built from particles with definite paths, with no mystery anywhere. Picture a surfer riding a swell. The surfer occupies one spot. The swell spans the whole bay. Where the surfer ends up depends on the entire shape of the water, including parts of the bay he never touched. The randomness you see comes from ignorance. You cannot control where inside the wave your electron started. Slightly different starting points, wildly different destinations. The statistics come out exactly matching quantum mechanics, provided the starting positions are distributed the way the wave says they should be. Bohm restored everything Einstein asked for. Definite properties, determinism, a real world running whether anyone watches or not. Now, the bill. The guiding wave for two particles lives in a space with 6 dimensions, 3 for each particle. Move one particle, and the wave shifts everywhere at once, including at the location of the other particle, instantly, at any separation. The theory is non-local, down to the bone, explicitly, unapologetically, written into the central equation. This is spooky action at a distance, promoted from an embarrassment to a founding principle. Bell adored it. He said Bohm's theory showed the vagueness and subjectivity of the standard view were avoidable, and that this discovery was one of the great shocks of his life. The theory is also what set him hunting, because he saw its non-locality and asked whether every hidden code needed one. His theorem answered yes. So Bohm's theory is safe from every experiment in this story. It was built non-local from birth. Bell's fence catches theories that stay local, and Bohm never was. The reason it stays in the corner is uglier than physics. It fights relativity. Instant influence requires a notion of now stretching across space, and relativity denies that any such notion exists. Bohm's theory needs a secret universal clock that no experiment can detect. It also predicts nothing new. Every measurement matches the standard theory exactly. You cannot test it. You can only prefer it. Which is why a small group of physicists went hunting for something that does make a different prediction. They found it by adding one more particle. Gerard 't Hooft won a Nobel Prize in 1999 for work on the mathematics of particle physics. He is one of the most respected theorists alive. He believes the universe is a machine that computes. His picture goes like this. Underneath everything, reality is a vast array of simple states, flipping according to fixed rules, like a colossal grid of cells updating in lockstep. Quantum mechanics is the fog you see when you look at that grid without the resolution to make out individual cells. And every measurement setting you will ever choose was already determined by the grid, along with everything else. This is superdeterminism, and it is the loophole that cannot be killed. Remember the third ingredient. Your choice of angle must be unconnected to the particles. Superdeterminism denies it. The particle's hidden instructions and your setting choice are two outputs of the same underlying evolution, correlated at the root, because everything is. If that holds, Bell's theorem proves nothing. The fence dissolves. Locality survives. Realism survives. Einstein wins, at a cost. The cost is your freedom, in a very specific sense, not the philosophical kind. The physicists here mostly do not care about free will. What they surrender is the assumption that you could have measured something else. Sabine Hossenfelder and Tim Palmer are the loudest advocates, and they argue the standard objection is lazy. That objection calls superdeterminism a conspiracy. Critics say it requires the universe to have arranged, at the beginning of time, a plot spanning quasars and laboratories and human fingers, all coordinated to fool us. The defenders say that word smuggles in an assumption. A conspiracy implies intent and implausibility. What superdeterminism actually claims is that the allowed states of the universe are constrained, and that constrained systems have correlations everywhere by construction. Nobody plotted. The state space is simply narrower than we imagine. Palmer builds his version out of fractal geometry, arguing that reality's allowed states form an intricate set with holes in it, and that the measurements Bell needs would require states sitting in the holes. Whether you find this desperate or elegant says more about your instincts than about evidence. Here is the part that matters. It might be testable. Hossenfelder proposed something concrete. If the outcome depends on hidden details of the detector, then measuring the same system repeatedly, faster than those details can scramble, should produce correlated results where standard quantum mechanics predicts fresh randomness every time. Cool the apparatus, measure quickly, and look for a pattern that should not be there. Others proposed modified Bell tests inspired by an odd laboratory system. Bounce a droplet of silicone oil on a vibrating bath, and it surfs on the waves it generates, and it starts imitating quantum behavior. It tunnels, it diffracts, it settles into quantized orbits. Those droplets show something like contextuality, using nothing but classical fluid. Picture a bouncing drop of oil reproducing the double slit in an open laboratory visible to the naked eye. That is what has some theorists convinced that a deeper mechanical layer is worth hunting. And in April of 2026, a group at a Quantum Studies Institute published something the field badly needed. They wrote down formal criteria for what makes a theory super deterministic, moving the debate off philosophy and onto quantifiable ground. For 60 years, this was an argument. It is becoming a specification. Meanwhile, a completely different attack was building, and it made the fence look generous. Bell needed thousands of trials and statistics. 3 particles need 1. Bell's fence is a statistical wall. You run the experiment thousands of times, count, average, and the violation emerges from the pile. That always bothered people. A hidden code sneaking a few % past the boundary feels like a technicality rather than a slaughter. In 1989, 3 physicists found something far more violent. Daniel Greenberger, Michael Horn, and Anton Zeilinger asked what happens with 3 entangled particles instead of 2. The answer broke the pattern completely. Here is the setup stripped to the bone. 3 particles fly to 3 separate laboratories. Each lab can ask its particle one of 2 questions. Call them the flat question and the sideways question. Each answer is +1 or -1. A coin flip either way. Now the labs coordinate. In one round, all 3 ask the flat question. In another round, one asks flat, and the other 2 ask sideways. Quantum mechanics makes a prediction so rigid, it has no wiggle room. Whenever exactly one lab asks flat and the other 2 ask sideways, multiply the 3 answers together. The product comes out +1, every single time, guaranteed. There are 3 ways to arrange that pattern, and all 3 obey it. So a hidden code has to reproduce that. Every particle carries an answer for flat and an answer for sideways, written before it left, and those answers must satisfy all 3 conditions with certainty. Now do the arithmetic. Take the 3 conditions and multiply them all together. On one side, you get +1, because +1 times +1 times +1 is +1. On the other side, every sideways answer appears exactly twice. Any number times itself is positive, whether the number is +1 or -1, so all the sideways answers cancel themselves out and vanish. What survives is the product of the 3 flat answers. The arithmetic has just proved that if all 3 labs ask the flat question, the product of their answers must be +1. Quantum mechanics predicts -1. With certainty, every run. No statistics, no averaging. The hidden code and the universe disagree about a single measurement, and they disagree perfectly. Picture 3 sealed boxes. You prove, using nothing but multiplication, that opening all 3 must give an even total. You open all 3. The total is odd, every time, forever. That is not a small excess. That is the instruction sheet being wrong about everything, in one shot. Physicists call this an all-or-nothing violation. Bell's twins argue about percentages. The triplets flip the sign. Building it took 11 years because entangling 3 photons is far harder than entangling 2. In 2000, a group in Vienna managed it. Jean-Wei Pan, working with Zeilinger and others, produced 3 entangled photons and ran the measurements. The universe delivered -1 exactly where any hidden code demanded +1. The instruction sheet was dead again, and this time the corpse had a bullet hole rather than a bruise. There is a deeper lesson hiding in that multiplication trick, and it goes further than distance or entanglement. The problem is not that the particles are far apart. The problem is asking more than one question at a time. Forget distance completely. Take a single particle, sitting alone in one room with nobody else involved. It still cannot carry an instruction sheet. Simon Kochen and Ernst Specker proved this in 1967, 3 years after Bell, and their results somehow stayed in the shadows for decades despite being arguably more disturbing. David Mermin and Asher Perez later found a version so clean you can play it as a game. Draw a grid. 3 rows, 3 columns, 9 boxes. Your job is to write a +1 or a -1 in every box, following 2 rules. Every row must multiply to +1, every column must multiply to -1. Try it. Take a pencil and actually try it, because the failure is educational. Fill the top row with +1, +1, +1. Good, the row works. Now the first column has to end in -1, so the 2 boxes below your first +1 must multiply to -1. Fine. Do the same for the second column. Fine. Third column. Fine. Check the bottom row. It gives you the wrong answer. Always. Fix the bottom row, and a column breaks. Fix the column, and another row breaks. The grid pushes the error around like a bubble under wallpaper and never lets you flatten it. Here is the proof it can never work. Multiply all 3 rows together. Each row gives +1, so the total is +1. Multiply all 3 columns together. Each column gives -1, so the total is -1 times -1 times -1, which is -1. Both calculations multiplied the same 9 numbers. One says +1, the other says -1. The grid is impossible. No assignment of fixed values exists. None. The arithmetic forbids it before you write a single symbol. Now the part that should make your skin crawl. Physicists can build that grid out of real measurements on a real particle. Each box corresponds to a genuine thing you can measure. Each row is a set of 3 measurements you can perform together, and quantum mechanics guarantees their product is +1. Each column is a set you can perform together, and quantum mechanics guarantees their product is -1. Every row works, every column works, every prediction gets confirmed in the laboratory. The universe wins a game that cannot be won. The escape is called contextuality, and it is uglier than anything Einstein imagined. The particle does have an answer for each box. The answer depends on which other boxes you check alongside it. Measure a box as part of its row, get 1 value. Measure the same box as part of its column, get another. The question changes the answer based on what company it keeps. Picture asking someone their favourite colour and getting a different honest answer depending on which 2 questions you bundle it with. Teams have tested this with neutrons, with trapped ions, with photons. The universe wins the grid game every time by margins beyond any doubt. So the hidden code fails even with 1 particle in 1 room, with no distance, no twins, no spooky action anywhere. Which raises a question that had been sitting in the corner for 80 years, waiting. If the particle has no fixed properties, what exactly is the wave function describing? Every quantum textbook draws a wave function and then refuses to say what it is. 2 answers have been fighting since the 1920s. The first says the wave is a real object out there in the world. It spreads, it interferes, it exists whether anyone knows about it. Physicists call this view ontic. The second says the wave is a record of what you know, a probability catalogue. Update your information, and the wave changes, the same way your odds change when a card gets turned face up. Nothing physical shifted, your ignorance shrank. This view is called epistemic. The epistemic answer is enormously attractive because it dissolves the worst puzzle in the subject. Consider collapse. A wave spreads across a room, you measure. Instantly everywhere the wave vanishes except at one point. If the wave is a real physical thing, something just changed across the whole room in 0 time, and that sounds insane. If the wave is information, collapse is nothing at all. You looked, you learned, your catalogue updated. Same as opening an envelope. Picture a detective who suspects 6 people. When the alibi arrives, 5 suspects vanish from the list instantly. No physical wave collapsed across the city. A mind changed. For 90 years, this was a matter of taste. In 2012, 3 physicists ended the standoff. Matthew Pusey, Jonathan Barrett, and Terry Rudolph published a theorem that hunts the epistemic view directly. Their reasoning runs like this. Suppose the wave really is just knowledge. Then 2 different quantum states, prepared differently, might describe the very same underlying physical reality. Your catalogues differ because your information differs, while the actual thing sitting on the table is identical. That overlap is the whole point of the epistemic view. Ignorance about the same reality is what makes different catalogues possible. Pusey and his colleagues took 2 such states, brought 2 independently prepared copies together, and designed a joint measurement with 4 possible outcomes. Quantum mechanics says one particular outcome has probability exactly 0. It can never happen. But if the 2 states share underlying reality, then sometimes both copies are secretly in that shared state, and when they are, the forbidden outcome has to occur with some real chance. 0 against non-zero. A flat contradiction. So the wave cannot be pure knowledge about a deeper reality. Distinct quantum states must correspond to distinct physical situations. The wave function is real, or something very close to it. The theorem lands hard, and it carries an assumption worth staring at. It requires that 2 systems prepared in separate laboratories have independent underlying states. Prepare one here, prepare one there, and their hidden realities do not overlap. That sounds obvious. It is also exactly the ingredient superdeterminism denies, so the escape route is the same one as before, which tells you something. The last shelter for a hidden code, again and again, is the claim that nothing in this universe is ever truly independent of anything else. Push on that, and the field starts asking a question that sounds like a joke and is deadly serious. Einstein once asked a colleague whether he really believed the moon exists only when somebody looks at it. Somebody built a machine to check. Anthony Leggett and Anupam Garg asked a question in 1985 that Bell never touched. Bell separated his particles in space. What happens when you separate the measurements in time? Take a single object. Watch it at 3 moments. Ask a yes or no question each time. Does the current flow clockwise or counterclockwise? Is the spin up or down? Now write down 2 beliefs that every sane person holds about ordinary things. The first belief: the object is always in one definite state. A coin on a table shows heads or tails. Right now, whether you look or not, it has a value even while nobody checks. The second belief: you can check gently. It is possible, at least in principle, to look at something without disturbing what it was doing. Glancing at a coin does not flip it. Leggett and Garg took those 2 beliefs, exactly as they took Bell's 3, and squeezed out a number. If the object really has a definite value at all times, and you can peek without wrecking anything, then the correlations between your 3 measurements have a ceiling. Compare moment 1 with 2 and 2 with 3 and 1 with 3, combine them the prescribed way, and the total can never exceed a certain value. Quantum mechanics predicts it exceeds it. The result is a Bell inequality running through time instead of across a room, and physicists call it a temporal Bell test. The best versions use superconducting circuits, those cold loops of metal that carry current both ways at once. In 2010, a French group ran continuous weak measurements on such a circuit and watched the temporal correlations climb past the ceiling. Teams have since repeated it with nuclear spins, with photons, with atoms, with quantum computers. The ceiling breaks every time, so at least one of those 2 ordinary beliefs is false for the systems tested. Now the honest part, because this is where the popular retellings go wrong. The second belief has a hole in it, and the hole is enormous. Physicists call it the clumsiness loophole. Suppose your measurement is simply rough. Suppose you thought you were peeking gently, and you were actually shoving the system around. Then the correlations break because you broke them, and the whole result says nothing about whether the object had a definite state. Proving a measurement is truly gentle is fiendishly hard. Every technique invented so far leaves the defender an argument. You were clumsy. You just cannot see how. So the temporal tests are suggestive rather than final. They constrain the belief that a small object sits in one definite condition between glances, and they leave a door open that engineering keeps failing to shut. And notice how far the scale has drifted. Bell's twins were photons. These circuits are visible objects printed on chips, holding currents made of billions of electrons flowing in both directions at once. The strangeness has climbed out of the subatomic and onto a countertop. Which brings us to a man who spent his career finding the cruelest possible version of every question, and who once asked what happens if you decide what a photon is after it has already made its choice. John Wheeler liked to make people uncomfortable, and in 1978 he found a way to do it with a single sentence. Wait until the photon is already inside the machine, then choose what it was. His setup uses an interferometer, which sounds intimidating and is simple. A photon hits a half-silvered mirror. It can bounce left or pass right. Both paths travel across a table and meet again at a second location. If you place a second half-silvered mirror where they meet, the 2 paths merge, and the photon shows interference, proving it explored both routes. Wave behavior. If you remove that second mirror, the 2 paths stay separate, and the photon lands in one detector or the other, telling you exactly which way it went. Particle behavior. Standard teaching says the photon decides which kind of thing to be based on the apparatus. Mirror in, it acts as a wave. Mirror out, it acts as a particle. Wheeler asked the obvious wicked question: when does it decide? His answer was to insert the second mirror after the photon had already passed the first one. The photon commits to its behavior at the entrance. You change the exit while it is in flight. If the photon somehow knew the setup in advance and chose accordingly, this breaks it. There was nothing to know. The setup did not exist yet. For 30 years, this stayed a thought experiment, because the photon crosses a laboratory table in nanoseconds and no switch was fast enough. In 2007, a group near Paris built it. Their interferometer ran 48 meters, giving them about 160 nanoseconds, and they drove the choice with a genuine quantum random number generator making its decision while the photon was already inside. The photon behaved exactly as the final configuration demanded, every time, as if it had known all along. In 2015, a team in Australia did something meaner. They used atoms. A single helium atom cooled to nearly absolute zero dropped through a grating made of laser light. Then a random number generator decided, after the atom had passed, whether to add a second grating. An atom is a massive object with internal structure, thousands of times heavier than any photon. The atom obeyed the choice made after its journey. Now be careful, because this is where the story gets abused. The experiment does not prove the present rewrites the past. What it proves is narrower and stranger. Any picture where the particle picks a definite behavior at the entrance and carries that decision through the machine fails. The photon crossing the table has no fact about which path it took. The fact comes into existence with the measurement, and asking what happened before the measurement is asking about something that was never there. Wheeler drew a cartoon to make this concrete. Imagine light from a quasar bending around a massive galaxy, taking two paths around it, arriving here after billions of years. Choose your equipment tonight, and you decide whether that light travelled one side or both. Ancient light. A choice made this evening. He was serious. The geometry works. And there is a version of this that goes further, where you destroy the evidence after the fact and watch the pattern reappear. Marlon Scully proposed something in 1982 that reads like a magic trick, and it fooled a generation of popular science writers, including a lot of good ones. Start with the double slit. Fire photons at two slits. Watch stripes appear on the screen. Now mark them. Put a tiny device at each slit that records which one the photon passed. You're not blocking anything, you're just tagging. The stripes vanish. Once the path information exists anywhere in the universe, the interference dies. Scully asked what happens if you erase the tag. Suppose the tag is stored in a second photon flying off to a different detector. Suppose you can measure that second photon in a way that destroys the witch path information rather than revealing it. Do that, and the stripes come back. Now make it cruel. Send the tag photon on a longer journey, so you make the erase decision after the first photon already hit the screen and left its mark. The mark is made, the record is on the screen, and then you decide whether the stripes exist. A group in Maryland built this in 1999. The results came out exactly as predicted. This is where the retellings go off a cliff. They say the future reached back and changed the past. They say the screen rewrote itself. Look at what actually happens. The screen never shows stripes. Not once. Not in any run. If you look at the raw pattern from the first detector, it is a smooth, featureless blob, always, regardless of what you do with the tag photon. The stripes only appear when you sort. You take your list of screen positions, you take your list of tag photon results, you match them up, run by run, and split the screen data into piles according to what the tag photon did. Sort into the erase pile, and stripes appear inside that subset. Sort into the other erase pile, and stripes appear too, shifted over by half a stripe. Add the two piles together and the stripes cancel exactly, giving back the featureless blob you actually saw. The pattern was always sitting there, cut into slices, invisible until you knew which slice each photon belonged to. Picture a deck of cards dealt face down into a heap. The heap looks like chaos. Sort it by suit and beautiful order appears. Nobody rearranged the cards after dealing. The order was inside the heap the entire time, hidden by the mixing. The sorting requires the tag photon results, and those results travel to you by ordinary means at ordinary speed. No signal moved backward, no past got edited. What the eraser really demonstrates is that which path did it take has no answer sitting in the world waiting to be found. The correlation between the two photons is the only fact there is, and it holds whether you look at it early, late, or in a different order entirely. That is disturbing enough without inventing time travel. So the accounting works. Every experiment stays consistent. Nothing signals backward. And yet a much older problem has been sitting under all of this, untouched since 1961. If a measurement creates the fact, then what counts as a measurement? And what happens if the thing being measured is a person? Eugene Wigner asked a question in 1961 that his colleagues found so unpleasant they mostly pretended he had not asked it. Put a friend in a sealed laboratory. Inside, the friend has a photon that could go two ways. She measures it. She sees a result. She writes it down. From her point of view, something definite happened at a specific moment. Now stand outside the sealed door. You know quantum mechanics. You know the equations describe everything, including your friend, because your friend is made of atoms, and atoms obey the theory. So you write down the wave function of the entire laboratory. The photon, the detector, the notebook, and the friend, all together, as one system. And your equations say the whole lab is in a superposition. The photon went both ways. The detector clicked both ways. The notebook records both answers. Your friend saw both results. She is certain she saw one thing. Your mathematics says she saw both. This is Wigner's friend, and it has a quality that separates it from every puzzle so far. There is no missing detector efficiency to fix, no loophole to close with better engineering. The theory contradicts itself depending on where you stand. Wigner drew a conclusion that most physicists refuse to touch. He decided consciousness must be special. A machine can be in superposition. A mind cannot. Somewhere in the friend's awareness, the wave function truly collapses, and physics needs a new law to say so. Later in life, he abandoned that view because it leads somewhere awful. If a conscious mind collapses the wave, then a lone conscious mind can be certain only of itself, and everything else becomes a question mark. Now, here is why this stayed a bar argument for 50 years. To test it, you would have to do something monstrous. You would have to measure the entire sealed lab, including your friend, in a way that reveals the superposition. That measurement would have to reverse everything that happened inside, unwinding the friend's memory back to the moment before she looked. She would have seen a result, then the result would be gone, along with her memory of it, and the lab would be back in superposition, ready for you to observe interference. Picture unbaking a cake, retrieving the eggs intact from the sponge, and proving the whole thing had never really been mixed. To do that with a human being, you would need to control every single atom in her body and her laboratory, with no leakage of a single photon to the outside world, because one escaped photon carries the information out and destroys the whole trick. That is beyond impossible. It is beyond every technology anyone can imagine, which is exactly why the puzzle sat untouched. Then, in 2018, two theorists in Zurich did something clever. They stopped trying to reverse a human. They added a second lab, a second friend, and a second Wigner, and let the four of them reason about each other, and they proved something that should have been impossible. Quantum mechanics, applied to observers who are themselves quantum systems, produces a flat contradiction. Daniela Frauschiger and Renato Renner published a paper with a title that reads like a threat. Quantum theory, they wrote, cannot consistently describe the use of itself. Their setup uses four agents, two friends, sealed in two labs, two outside observers, one watching each lab. Each agent uses quantum mechanics correctly. Each one reasons about what the others must conclude. The chain goes around. The first friend deduces what the second friend must know. The second observer deduces what the first friend must have seen, and so on. Every step is a legitimate application of the theory. Run the chain, and in a small fraction of runs, two agents reach opposite conclusions about the same physical fact. One is certain the answer is heads. The other is certain it is tails. Both are correct by their own impeccable reasoning. The contradiction survives if you hold three assumptions: that quantum mechanics applies to everything, including observers, that every measurement produces one outcome, that agents can trust each other's conclusions. One of those has to break. Look at what each choice costs. Drop the first, and you are claiming quantum mechanics stops working somewhere between an atom and a person, at a boundary nobody can locate. Drop the second, and you have accepted that measurements produce many outcomes in many branches, every branch real, every version of you real. Drop the third, and you are saying a fact established in one laboratory is simply not a fact anywhere else. Reality becomes local to the observer. Every exit is a demolition. In 2019, a group in Edinburgh led by Massimiliano Proietti built a version. They could not seal a human in a lab, so they did what physicists always do when the object is impossible. They shrank it. Their friends were single photons, 6 photons in total. 2 played the role of the systems being measured, 2 played the friends, each one measuring its partner by becoming entangled with it, which is precisely what a measurement is at the mechanical level. 2 more served as the outside observers. Then they ran a Bell-style test across the whole arrangement, comparing what the friends recorded against what the outside observers found. The inequality broke by 5 standard deviations. Another group in Australia, working with a stronger version of the theorem, ran their own experiment and found the same thing. The results say that the facts recorded by the friends and the facts recorded by the observers cannot be assembled into one consistent story of the world. Now, the fight. Critics landed on the obvious weak point. A photon is not an observer. A photon has no memory, no awareness, no record you could ever call an experience. Calling a photon a friend is a metaphor doing very heavy lifting. The defenders reply that an observer, physically speaking, is any system that extracts information from another and stores it. By that definition, the photon qualifies. The argument is unresolved and probably unresolvable with current hardware. Someone would need a friend big enough to genuinely count as an observer and small enough to keep isolated from every stray particle in the universe, which is the same wall this entire field keeps hitting. Where does the quantum world end? A group of physicists decided to stop asking and start hunting for the edge with a detector. 3 Italian physicists proposed something in 1986 that most of their colleagues found offensive. Change the equation. Every interpretation so far accepts quantum mechanics as written and argues about what it means. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber said the theory itself is incomplete, and that a small extra term fixes everything. Here is the idea, and it is beautifully blunt. Every particle in the universe gets randomly yanked into a definite position at random moments, all by itself, with no observer required. The yank is called a spontaneous localization. It obeys a fixed rate written into the laws of nature. Set the rate absurdly low. A single particle suffers one of these jolts roughly once every 100 million years. That is why a lone electron sails through a double slit undisturbed. The odds of a jolt during its flight are essentially 0. Now add the amplification, because this is where the model becomes clever. Particles bound together share their fate. Jolt one atom in a rigid object, and the whole object localizes with it. So the collapse rate multiplies by the number of particles. A grain of dust has more atoms than there are stars in 1 billion galaxies. Run the arithmetic, and a dust grain in superposition collapses in a fraction of a second. Picture a lottery where a single ticket wins once every 100 million years, and a corporation holding 1 trillion tickets wins several times before you finish this sentence. One equation, and the entire measurement problem evaporates. Small things stay quantum because they rarely get jolted. Big things become definite because they get jolted constantly. There is no observer, there is no consciousness, there is no boundary anyone has to draw. The friend in the sealed lab sees one result because she contains too many atoms to stay in superposition for even a blink. Here is why this proposal outranks every other idea in this story. It makes different predictions. Every other option is a reinterpretation. Bohm predicts the same numbers. Many branches predict the same numbers. Superdeterminism predicts the same numbers, mostly. You can prefer them. You cannot test them. Collapse models change the equation, so they change the world, and the changes leave fingerprints. The jolts add energy. Every spontaneous localization shakes a particle slightly, and shaking a charged particle makes it radiate. So a collapse model predicts that ordinary matter, sitting perfectly still in the dark, glows faintly with radiation that standard physics forbids. It also predicts that isolated objects warm up on their own. Free particles diffuse when nothing is pushing them. Every atom in the universe carries a tiny, permanent, unexplainable jitter. Suddenly, the deepest question in physics has become an engineering problem. Find the glow, measure the jitter, confirm or kill. Physicists have been hunting for 40 years. A spacecraft flying in the emptiness beyond the moon put limits on the jitter by measuring how a free-floating cube drifted. But the most powerful hunt for reality's hidden noise took place somewhere much stranger, under a mountain. Beneath 1,400 meters of Italian rock, in a laboratory built inside a highway tunnel, a slab of germanium sits waiting for light that should not exist. The mountain is there to kill everything else. At the surface, cosmic rays rain through every square inch of your body at a rate of dozens per second. Radioactive decay hums in the walls, the concrete, the air, the equipment. Any faint glow from a collapse model would drown in that racket instantly. So they went under the Gran Sasso Massif. The rock strips out cosmic radiation almost entirely. The detector sits inside layers of ancient lead, chosen because modern lead is contaminated with fallout, and old lead has had centuries to quiet down. Some detectors use lead recovered from Roman shipwrecks. Inside all of that, a germanium crystal counts photons. The team, including the theorist who first proposed a gravitational version of collapse, went hunting for the specific radiation that collapse models demand. Here is the target. If protons in the germanium get randomly jolted, they radiate X-rays. Standard physics says germanium sitting still in the dark emits nothing at that energy. Collapse models say there is a faint, steady, unstoppable trickle. They counted for months, and they aimed at one model in particular because one model has nowhere to hide. Roger Penrose and Lajos Diossi had proposed that gravity does the collapsing. Their reasoning is elegant. A massive object in superposition puts space-time itself into a superposition of two different curvatures. Penrose argued that space-time refuses to hold that pose, and that the tension resolves itself by collapsing the object into one location. The beauty of the proposal is that it has no adjustable knob. The strength of the effect comes from gravity, and gravity's strength is already known. So the model makes one prediction, with no room to wriggle. In 2020, the team published their count. The glow was absent, and their limits sat below what the model demanded. The simplest version of gravitational collapse died under a mountain in Italy, killed by radiation that failed to arrive. Penrose's idea survives in modified form, if you smear the mass over a minimum distance and choose that distance carefully. The parameter-free version, the clean one, the one that had no escape, is gone. The same measurements squeezed the other collapse models hard. The Italian trio's original proposal survives in a narrow band. The most popular continuous version survives in a shrinking corner of its parameter space, hunted from one side by these underground counts, and from the other side by interference experiments proving that large objects stay quantum. The vice is closing from both directions. This is what makes collapse models the most exciting idea in the whole story. Physicists are not arguing about them. They are killing them, one parameter at a time with detectors and patience. The parameter space has a flaw, and the flaw is where the theory has to fail entirely. If the noise is real, someone will find it. If the noise is absent, the models die completely, and physics will have to admit that the wave function never collapses at all. And the other jaw of the vice, the one closing from above, is doing something nobody expected. It keeps making bigger things behave like waves. In a Vienna laboratory, a molecule made of 2,000 atoms went through two slits at once. Marcus Arndt has spent his career pushing the double-slit experiment up the weight scale, one molecule at a time, and the results should be impossible. The story starts in 1999, when his group sent a soccer ball-shaped carbon molecule, 60 atoms strong, through a grating and watched interference fringes appear. That molecule already has internal structure, vibrations, and heat. It radiates. It should be far too complicated to behave like a wave. It behaved like a wave. Then they went bigger. In 2019, his team fired molecules built from 2,000 atoms, weighing 25,000 times more than a hydrogen atom through their machine. The fringes appeared. Understand what those fringes mean. Each of those molecules is a floppy, complicated, warm chemical structure, larger across than many small proteins, and every one of them took every path through the apparatus simultaneously, then interfered with itself, then landed on the detector in a pattern that only a wave can produce. The engineering is savage, the wavelength of a molecule that heavy is smaller than the width of a proton. To see interference at that scale, the machine had to hold its grating steady to a fraction of that width, for the 2/3 of a second the molecule takes to cross. 2/3 of a second sounds trivial until you remember what it means. For 2/3 of a second, an object you could almost call a speck was in two places at once, and stayed there. Picture a bumblebee, if a bumblebee were mostly wave, drifting through a fence with two gaps and coming out the other side having used both. Every one of these results tightens the noose on collapse models. If reality carries hidden noise that destroys superposition based on how many particles you have, then 2,000 atoms should have been enough to break it. The fringes should have washed out. They did not. The models get pushed into weaker and weaker corners, and the race continues in the other direction. Teams are cooling glass beads, sapphire crystals, and vibrating drums until they reach their quantum ground state, then trying to lift them into superposition. A crystal you can see under a microscope. Objects heavy enough to weigh on a laboratory balance. Every kilogram of progress is a direct assault on the idea that a hidden mechanism kills the quantum world above some size. So here we are, after 60 years. The instruction sheet is dead. Distance failed to save it, and neither did starlight, quasars, or 100,000 strangers. Contextuality kills it even with one particle in one room. The wave function looks like a real object. Observers can be made to disagree. Gravity does not collapse anything, at least not the way Penrose wrote it, and the quantum world keeps swallowing bigger and bigger pieces of the ordinary one. One thing in this universe has never been tested at all. Gravity has never been shown to be quantum, not once. Every experiment that touches it treats it as a smooth classical background, exactly as Einstein described it. There is an experiment being built right now to settle that, and it is the strangest thing anyone in this story has ever attempted. Everything in this story has been about particles. The final experiment asks the question about the stage they stand on. Here is the gap nobody talks about. Physics has two great theories. Quantum mechanics describes matter. General relativity describes space-time, and it describes it as a smooth, definite, classical thing. A sheet that bends. Nobody has ever seen gravity behave quantum mechanically. Nobody has ever detected a graviton. Nobody has ever caught space-time doing anything uncertain. For a century, physicists assumed gravity must be quantum because everything else is, and a classical stage holding quantum actors leads to contradictions. It is a very reasonable assumption sitting on zero evidence. In 2017, two groups proposed a way to check. Sugato Bose in London and Chiara Marletto and Vlatko Vedrol in Oxford arrived at nearly the same idea at nearly the same time. The logic is a joule. Take two tiny masses, put each one into a superposition of two positions left and right. Now hold them near each other, so the only thing connecting them is gravity. No light, no air, no electric field. Gravity alone. Each mass feels the other's pull, and the pull depends on where the other one is. Left mass with left mass, they sit close. Strong pull. Left with right, farther, weaker pull. Each combination picks up a slightly different twist in its wave. Now bring each mass back together and check. If the two masses end up entangled, gravity did it. And here is the killer. A classical field cannot create entanglement. That is a theorem, not an opinion. If you can only push a message through a middleman, and the middleman is classical, then no entanglement can ever appear between the two ends. So entanglement between the masses proves the middleman was quantum. Space-time would have been caught in superposition by its own fingerprints, without anyone detecting a graviton at all. Picture two people in separate rooms, connected by nothing but a rope through the wall. If they end up sharing a secret that only a quantum channel could carry, then the rope was quantum, whether you ever saw the rope or not. Now the reason it has taken a decade and counting. Gravity between two specks is the weakest force anyone has ever tried to use. The masses need to be heavy enough to pull on each other measurably, and light enough to hold in superposition. Those requirements fight each other viciously. Current designs call for diamond specks around 100,000th of a gram, split into superpositions tens of micrometers wide, held for several seconds, at temperatures within a whisper of absolute zero, in a vacuum emptier than interstellar space, shielded from every stray electric charge and every passing cosmic ray. Any single stray photon striking one speck destroys the entire run. Teams in Britain, the Netherlands, and elsewhere are building the pieces now. Nobody expects a result soon. If it works, one of two things happens. Entanglement appears, and space-time joins the quantum world, and the century-long divorce between our two great theories finally has a path toward reconciliation. Or entanglement fails to appear, and gravity is genuinely classical, and everything we thought we knew about unifying physics collapses at once. Either answer rewrites the foundations. Einstein started this by insisting reality had a hidden layer underneath. 60 years of experiments proved his particular version wrong in every direction, at every scale, using starlight and quasars and diamonds and mountains. And the final experiment in the entire saga uses his own theory of gravity to ask whether the deepest thing he ever discovered plays by quantum rules. Somewhere out there, 2 diamond specks are waiting to answer.